engineer in the defense industry. And so my background, I actually started off as a computer engineer. So I worked in a research lab writing firmware. And a lot of my hardware experience actually comes from like debugging and working with that, because with firmware, you're interacting a lot with the hardware. Since it was a research lab, there was a lot of different prototypes, a lot of different versions coming on my desk, and things didn't really work out the way that they needed to. And sometimes you had to like make something to interact with the board or finagle it in the way that you needed it to work. And so now hardware reverse engineering is kind of like a hobby slash professional trade of mine. And so I'll kind of go into what it is, how you can get started in a very beginner aspect, and hopefully you guys can learn something. So why reverse hardware? Everyone has their own motivations. And so what would your motivations be? Reverse engineering hardware gives you a chance to kind of explore different designs that would be in a hardware circuit. A lot of times when you learn from a textbook or you learn from videos, you kind of just learn how to build one circuit for one case. And so when you're trying to build something for something specific, you're curious, like, how does someone design it? This gives you a chance to kind of dive in and peek at what other people are doing. And also kind of gives you the power to learn how to repair your own electronics. Now, I don't suggest that, after like a few months, you go and pull out your GPU and you can go and try and fix all that yourself. Be wary about where your skill level is and what you're trying to fix. But if something's very simple, like all you have to do is solder on like a resistor or just fix a trace line, that's something very easy, something you don't have to pay somebody $50 or $100 to do. It's something you can do yourself. And also explore different devices that you probably see around that yourself, and see if there's any bugs in that or if there's any backdoors. I mean, I know there's like a lot of things going on with entities putting in backdoors into electronics to collect information. And so you can kind of dive in and see if there's any nefarious things going on. So I'll break this talk down into 3 different sections. So taking apart enclosures. So devices aren't out in the open unless you're buying a board, the dev board yourself. Usually you have some sort of enclosure that you have to take apart, and it's not so straightforward as you think if you want to keep things nice. Identifying components. So once you open up the hardware, what are you looking at and what should you be trying to find on the get-go? And interfacing with the hardware. So how can you talk to the hardware? How can you kind of see what's going on and what it's saying? And with each step, I'll kind of go into like the tools you'll need. And so hopefully it won't be just a big dump of tools and then not really knowing how to use them. Okay, so first things first, safety. So anything that plugs into the wall is high voltage and high current. It actually takes very, very little current. I think it's like 10 milliamps across your heart to kill yourself. So you definitely want to be wary. You want to be wary of lithium batteries. If they look like they're expanded, or if you're working with like something, like if you have an unstable power supply and you're trying to work with a circuit with the battery still connected, don't do that. Just disconnect the battery. If it looks expanded, find a safe way to discard it before before it explodes in your face. Those things are scary. And so what can you do to keep yourself safe? So even if some hardware is unplugged, it can still hold a charge because of capacitors, because of different components. And so give some good amount of time to wait for it to discharge. I work with very low voltage stuff. I think like 12 volts is the max. High voltage things, like maybe like a TV or those really old CRT TVs that happened in the olden days. I guess back in my days, those can take even longer to discharge. So depending on the components, don't assume that just because it's not plugged into a wall or plugged into a power supply that it's safe to touch. Remove jewelry and tie back your hair before you're working on stuff. wear rubber gloves or use a rubber mat in the work area that you're working on your hardware, and make sure everything's dry, your area. And one trick is to use one hand. So don't dive in with both hands touching the circuit. Use one hand and keep one in your pocket when you're working with high voltages, especially if you're working with things that plug directly into the wall, or if you see those big capacitor things, be careful. Keeping your hardware safe. And so many electronics are, I guess, susceptible to electronic static discharge damage. And so if it has, so, you're shuffling around on the carpet, you accidentally kind of like get near it, you're going to shock that thing and probably going to damage the hardware. How can you prevent that? Don't be like me. So there's my work desk back there. You can see there's carpet. Don't be like me. Don't work in the area where there's carpet. Try and put like a rubber mat down. One trick is to like touch some metal before you start working on something so you can discharge yourself. Use an ESD safe mat, and then preferably one that works well with heat. If you're going, because you're going to be soldering, you're probably going to be using a heat gun. So you want it to be ESD safe. You want it to be heat resistant to a degree. And you can discharge your ground stuff again with touching hardware. There are like wrist straps, grounding wrist straps. And so if you want to be like super heavy duty, you can go and like ESD safe your workstation. So you would be plugging in the mat and your wrist to a grounding line that most of your station would be connected to. Though it's not necessary, especially when you're starting out and you're working with I guess not too sensitive hardware. And store your hardware in ESD safe bags, but don't place it on top. Those bags are actually, they're conductible and usually they dissipate charge to the outside of the bag. So you don't want to be placing it on top because you can still damage your hardware that way. So once you pull the hardware out of the bag, put the bag to the side. All right, so keeping yourself legally safe. So usually people don't like it when you go and you dig into their IP and put it out in the open, tell them what bugs they have. So, check what the end user license agreement says and terms of service for that device. Maybe, there's this link, EFF.org, that go into the whole laws and codes, to bug hunting, to reverse engineering. Just make sure that you talk to a lawyer, check these things out before you release them out to the public, so you don't get yourself into a legal bind, especially right now with the whole, repair rights and all those things going on. You want to keep yourself legally safe. All right, so let's dive in with taking apart enclosures. So first, everything is usually put together with a screw. That's not always the case, but you can just go online, maybe Amazon, and get get like a screw head pack. I know people recommend the iFixit pack. I got this for like $10, and it has every screw that I ever really needed, except this one was a big nifty screw I had to get a special tool for. And so keep an eye out where screws are hiding. There can be hiding under like foot pads is a popular place to put them, under stickers. And like this one it's a little bigger than the star screw head in these. So I had to go and, get it wasn't proprietary screw, but you might have to go and find a specialty screw for whatever hardware you're trying to take apart. All right, so getting around clasps and adhesive. So today it's really, really popular to just have something enclosed with this thick, down here you see this thick tape that's kind of keeps everything together. So you would want a heat gun for that to heat it up, kind of soften the material. I tried doing it with just a shim and pulling it out. It's not that easy. I just wanted to try it out and see how hard it is. It's hard. I cut my finger just from holding the shim so tight. So, be careful. And these ones also like a few bucks. This I call it the guitar pick. People call it a plectrum. And so this one's really good for trying to take apart clasps that you sometimes things are also clasped together, and so you kind of have to release those by just kind of yanking them out. So to help you, I mean, a lot of times there's a lot of teardown videos for the specific device. You want to be careful with heat and excessive force. You can definitely break the device that way. You can break the screen, and there be glass, and you can cut yourself. So be careful with that. And you can kind of tell. Don't be too forceful. Try and have a gentle hand with it, and you can feel the resistance that something gives, and just be smart about it. And sometimes it's going to be inevitable to damage something. So right here is the TP link. It's a little travel router, and so it's actually, this is where you'd put the shim in around this little bevel. I thought it was just going to be clasps, and I can just use the guitar pick and kind of release it and pull it open. But actually, if you look, these things were actually melted together. So they were soft before they smushed these two parts, and when it cooled down, it's there. So if I want to put this thing back together, I'm probably going to have to use some glue. Also, be wary of what tool you're using. So you don't want to use a tool that's too soft for the device that you're trying to open, especially if you're trying to shim, because then you're just going to ruin your tool. You also don't want to use something that's too hard, because right here, I was repairing my laptop. I was using, I think I was using a metal shim. And so now I have these bevels on the side. So you want to be wary, make sure that the softness, the malleability of your tool and of the enclosure you're trying to open is appropriate for each other. You kind of want to try to get a more or less the same. All right, removing connectors and shields. You're going to need a heat gun and a soldering iron, and you're probably going to need really good reworking skills and soldering skills. So this is Kindle Fire, and these are EMI, so electric magnetic interface shields that are usually around components that they're trying to that are high frequency, and they're trying to reduce noise and interference. These are a pain to get off. As you see right here, I removed the EMI shield on the bottom right. I actually damaged the board. So use the heat gun, use a lot of flex, try your best, have some tissues for your tears, because they're a real pain to get off. But before even all this, when you're opening the device, be careful about any ribbons or any things that might be connecting the things together. You don't want to just yank things open right away. You have to be aware, take a peek, make sure everything's disconnected before you pull two pieces apart. Also, be aware of what clasps are being used. So a lot of times with these ribbon connectors, there's usually a terminator clasp, and you just press in and it locks. But with this case, they have a folding one, so you actually fold it down. I found that really interesting. And there's also these ones usually are used to the ones that just plug in together. These ones are actually, you lift them up, so you have to get some tweezers from the sides and lift up the connector from there. Yeah, so also so I like to go and to secondhand stores or get people's old devices just to get familiar with things without having to damage something that's working. But what happens to be the case is that things tend to be full of dust and cobwebs and spiders and bugs. So another tool that's nice to have is a vacuum, maybe with one of those detailer hoses so you can suck them all up. Open space, don't do it in your room because it's going to get dusty and gross, and you're going to find some interesting things. And compressed air helps as well. Okay, so hardware is open, it's there, it's on your lab desk. So what do we do next? So what you'll need is a microscope. Those tend to be expensive, so I just use a driller's loop. You're going to need Google data sheets. an oscilloscope for looking at different data lines, different analog lines. You're going to need a multimeter and a schematic tool. So as you're kind of figuring out how things are connected together, you're going to want to, I recommend at least trying to draw out the schematic as much as you can. You know, some people use KiCad Eagle. That way, you know, there's a library that's already there. But sometimes it kind of gives you, you know, warnings. There's a learning curve. So you can also use like Visio or like LibreOffice Draw. LibreOffice Draw is free. And so you don't have to deal with learning curve. You can just draw things out as you're dealing with it. And you can probably go to a schematic later if you're worried about, or if you want to go and build things up yourself into your own PCB. Okay, so identifying components. So first thing you want to go and look at like the IC chips, and IC chips are on these little black packages that you see here. And they all have like these serial numbers and IDs up top, and you can go and Google that and see what the component is. So here we have a network transformer, which all that does is kind of just condition the lines for the Ethernet port right here. We have Giga device. We have flash memory. Awesome. So that's, you know, that's of interest to us. And we also have a MediaTek Wi-Fi sock. So this is a Wi-Fi chip. And so instead of having like something to interact with the Wi-Fi components and a separate microcontroller, they put it all into one specific use package. It saves on money, saves on power. So this is popular with like routers and repeaters, tiny routers and repeaters. And so cool. So we see the brains. I did not open this EMI shield right here. It looks pretty hefty. I didn't want to damage this board because I still want to use it. And there's this really heavy duty ceramic heat sink up top too. So I left that closed. And, you know, we'll get into trying to figure what's underneath that later. And so once you look up these data sheets, you can, you know, I kind of work from, I guess, inside out. So, you know, what's connected to what? So we look at these external connectors. You want to figure out, you know, what pins are connected. I'm assuming that, you know, since this is the brains of the thing, what pins are connected to, you know, this USB to look at a UART port right here. That's of interest to us. What you can do is use the multimeter. Let's see if I can put this up right here. So you see that you can look at voltage, amperage, but there's also like this little diode symbol up here that can help you. It's the connectivity. So this one was like $5. I'm going to be using the one that I use. It's the same exact thing. You don't need anything heavy duty, especially when you're starting out. But when you connect two traces, when you touch two lines together and they're actually connected, you hear like a beep. Let's see if you can hear it. No. It's not coming up on the mic. It is not. Well, it's a big beep. It's a big annoying beep, but not big enough for the mic. And so you can just create your schematic from there, going from, you know, line to line, seeing what's connected together and building up your schematic. And so, yeah, once you get everything, you want to look up the components. So the serial flash, we can see, okay, so it's a serial flash and it, you know, it talks over SPI. And so we see each different line. You see serial clock, chip select, serial data in, serial data out, and so forth. Okay, this is of interest to us. Also, with these manuals, a lot of times they give circuit designs, recommended circuit designs for different things. So a lot of times you see it with a microcontroller, how they recommend, you know, doing the power supply, how they recommend connecting specific components to the microcontroller. They give a recommended circuit. And engineers, if this is what the manufacturer is recommending, an engineer is going to go with that. So it gives you a lot of information of what's there, how the circuit's going to look like, and that's very valuable. Also, with wireless devices, you can look up using the FCC ID, you can kind of look up information. So if it's transmitting something, it's going to have an FCC ID. If it's receiving, it'll probably have the FCC logo, but you'll know that there's another device that's made to talk to it. Not a lot of times do receivers have the FCC DID. If it's a paired device, it's really just the transceiver. So just keep that in mind. But if you just go to FCCIDIO, which is a website that was created to kind of deal with the .gov website, since that one's a little messy, and type in this ID, we have all of these data sheets. And this has a lot of information. It tells us, how the device talks, what frequency range it is, all the other going ins. And hey, look it, I found what is underneath that heavy duty EMI shield that I didn't want to take off. So we see that we have the RF chip, we have 2.4 gigahertz antennas that are embedded into the board, and a 5G antenna. Here, I'll bring it up right here. You can't see it right there, but there's like a little cute antenna that's right here. And so, now we know what's underneath, and we didn't have to look. I didn't have to take it apart myself. And I found this kind of funny. They couldn't even take off the EMI shield without damaging the board themselves. So it's not just me, and it's not just that one. There's one up there too. All right, so everything's open. We kind of have an idea how the device works to a degree. We know what components are on the board. And for the TP link, we kind of have a IC of interest, the flash chip, so we can just pull off the software from there. So how do we actually interface with this thing now that we are familiar with it? Things you'll need a power supply to power it on, an oscilloscope to look at data lines, a logic analyzer to also look at data lines. And so logic analyzer only looks at digital data lines, where an oscilloscope, you can look at different signal lines that are also analog and digital. A function generator. So this was very handy when I was debugging hardware. The hardware I was working with interacted with a sensor. And so a lot of times I didn't have the sensor, but you still want to kind of test out the circuitry and the different components on the board without having to have the sensor on the board. And so function generators you can feed in a signal into a circuit and see how it behaves. And it gives it can help you get very valuable information on what a circuit's trying to do and how it's working. Also something to interact with the device, like a bus pirate, or you can have an Arduino or an FPGA, depending on how high skill level you want to be. But there's different devices out there that can help you interact with specific protocols and specific bus lines. And so let's go into common ones that you'll see. So UART and RS-232. So UART is the same as RS-232. UART is just a little bit more specific into what the protocols and standards entail. And so you'll have a transceive and a receive line. And so the transceive line of this device is going to go to the receive line of the next device that's trying to communicate to, and vice versa. And so it's just a single. Whereas some other serial lines, such as RS-422, they call it, there's differential lines, which means that you'll have the positive signal and also kind of like the inverted signal on another line. This is just to help with noise, to help with redundancy, to help pick up errors for the data that you're sending and receiving. And usually for this, there's FTDI, so you can plug it into your computer. Well, it doesn't really have transcribed, but you have your ground, your power, your send and receive, and it converts the RS-232 signal to a USB so you can kind of interact with that comms line from your laptop through like a shell or putty. And so a good trick is so baud rates are predetermined when it comes to RS-232, UART, RS-422. And so, instead of trying to like guess, there's usually like, 4 or 5 baud rates that are very common. Instead of guessing between those two, a smart way to do it would be to get an oscilloscope, look at that line when data is running across it, and try and figure out the baud rate for yourself. And you can do that by just looking. So here you see the signal, you see data going through. You find the smallest square, and you measure it. And so you can see one's at 2.0 milliseconds and the other one's at 2.1, and you can calculate what the baud rate is, because baud rate is just bits per second. So easy calculation right there. And also be wary of the capability of your tools. So there's a lot of high data bus lines sometimes with hardware, like if you're interacting with like DDR, RAM memory. So usually you want to be at Nyquist rate. And Nyquist rate is basically if your device is talking at 2 megahertz, you're going to want twice that to be able to cleanly observe that signal. So you would want to have something that can talk at that can take in signals and see them at 4 megahertz. So be wary of Nyquist rate, be wary of the clock rates of the hardware you're looking at, and the clock rates of the tools that you have. Okay, there's also encodings. So be wary of that. So, there's non-return to zero, m0zy. And this is what we kind of assume, right, that the signal would look like, that when there's a one is high, when there's a 0, the signal's low. But there's different encodings, and encodings are there for different reasons. And so if you're looking at a signal and it's not looking, it's looking alien, it's not looking something that you would assume for it to be aware of different encodings. So sometimes it's inverted. m0zy actually changes every time there's a 1. So here's 0, here's 1, 0, once there's a 1, it goes up, and so forth. There's also, these are the kind of common ones, Manchester. And so it's good to know about clocks. So what does it mean? Like, how does a device know when it's 1 or 0? Like, where does it sample? Where does it sample the value of that data line? So here, this is sampling at the rising edge of the clock. It samples what the value is. So this is something that you can help you see what the encoding is. How does the rise and falling of a signal align with your clock? Other data lines that are very common is I2C and SPI. So I2C is a 2 data line bus, and you have your serial data and your serial clock. And you see here that you can have 2 lines with multiple devices on it. Usually there's one master, and you can have multiple slaves. You can also have multiple masters on this bus. And so it works by pulling up and down these different lines to kind of signify what's going to happen. Also, let's go to SPI first. So here, SPI is also very common. It's an easier protocol, though. It's very straightforward. So you have your chip select. So the master kind of selects which slave it wants to talk to by putting that select line high or low, depending on the chip. So you would have to have multiple chip select lines for the number of slaves that you would have. You'd also have a serial clock. You would have, here's m0zy, master out, slave in. You have master in, slave out. And then that kind of goes into the slave data in and slave data out. So here for SPI, you can only have one master. but you can have multiple slaves, but you would have to replicate lines to the number of slaves that you would have. I2C is a little bit more efficient in its data lines, but its downfall is that where master here, you can select which chip you want to talk to with the chip select line. This actually happens with a address. So it calls out its name, which whatever ID it has, like, hey, I'm going to talk to, 1, and I want to read or write or whatever. That takes up some of your bandwidth, but on the other side, you get to do more things with less data lines. So, these are 2 trade-offs, things to keep in mind. JTAG. JTAG is used a lot to program chips, to debug chips, like microcontrollers, FPGAs, and so forth. And a lot of manufacturers use a whole bunch of different, JTAG connectors, but the standard ones are test clock, test mode select, test data in, test data out, and then resets optional. So, so really it's these 2 that are talking the most, but you definitely need all 4 of these. And if you look at these different standards, so we have 2 from TI, 1 from ARM, and their various pin sizes, we see that all of these 4 are included in all of these heads. Some of them have a dedicated ground line for each signal line, some of them don't. And they also have some other things that are, some other data lines that are dedicated for their JTAG chip line. And so JTAG connectors, sometimes you'd have to get the specific debugger JTAGger for that device. Like if you're working with an AVR chip, you need an AVR debugger. If you're working with a PIC, you need a PIC one. There's also some generic ones that are out there. Sometimes they work well, sometimes they don't, and sometimes they're really expensive. Like the J-Link is an expensive JTAG device to get. I think they have a student one out there, but it's whatever you can get your hands on. So connecting to chips. Usually when you get like, a logic analyzer, I have this Salier. They have these really nifty little tiny clips that you can just put on these on the legs there. Sometimes the pins are much smaller than what you can connect. To deal with that, you can either what I call putting on pigtails, where you strip some wire, you solder it on to kind of bring out those pins that you can easily connect to with whatever the device you're using uses to connect, whether it's alligator clips or these. Or if the pins are very small, you can, people usually sometimes get sockets. Sockets end up being like $20, $30 per chip. I don't think that's very cost effective, mostly because, I'm working with this one device. I don't see like, each chip has a unique footprint, and I'm not going to be using this multiple times. So $20, $30 for a one-off isn't my style. I usually go with what's called a surfboard. You can either buy one or create one yourself. It ends up being like $2, $3, and you just desolder the chip, solder it onto the surfboard, and then now you have all these pins expanded out for you to connect to. Yeah. So, we're connected to the chip. So after that, once you connect to the chip, it's kind of you're home free. I'm using the bus pirate here. So I just do flash ROM, bus pirate. We see that before that it was talking over SPI, and we can, check the frequency by turning the device on, hooking up our oscilloscope, and looking what the frequency of that bus line is. And then just wait till the, software is pulled off, and then, now it's software interactions from there and reverse engineering that binary. If it's a JTAG, if you're connecting to a chip, you would use, there's OpenOCD, is open software. There's different tools you can use. I think the bus pirate can work with JTAG. There's better ones out there. The bus pirate's kind of slow. And so the stuff that we're looking at is kind of very rudimentary methods for hardware reverse engineering. The boards I've worked with tend to be like 2-layer boards. And what that is how many copper layers are in the PCB. The more layers in the board, the more complex it's going to be. You can't just do the multimeter trace line to get that, to try and build up a schematic. It's going to be very rigorous, very tedious, very time consuming. So professionals usually have more advanced methods like PCB sanding. So they sand down the PCB, sand down the silk, look at each layer as they're sanding down through the PCB. There's also X-ray and infrared. So they X-ray it to look at the different PCB layers from there. Also, sometimes chips don't really have markings that you can go and Google. So, sometimes they do that to kind of obscure things, and it actually is an off-the-shelf device. And you can kind of find out what it is by comparing it with other devices, looking at the footprint, looking at the pins and what each line is and compare with chips and what those lines are. And usually you can kind of find like what chip it is if that's the case. But sometimes what manufacturers and device designers do is build up their own ASIC for dedicated use. So how does somebody figure out what the chip is doing and how it's designed? They actually decap and have a very powerful microscope to look at the VLSI of that chip. So that's very, other interesting methods to kind of go and explore if you're curious. So there's a lot of tools that you need, and it's very expensive. Oh wait, no, that's not the slide. Let's go back. So there's a lot of tools that you use, and it's very expensive. So like, how do you go and, start off if you don't want to like drop a whole bunch of hundos on this? A lot of you guys are students, so there's on-campus labs. You can go and get permission to access, the tool, their oscilloscopes, their function generators, their power supplies. Those are available to you. I know during COVID that might not be the case, but things are starting to open back up. There's also hacker spaces. I know some of you guys are up in Dominican Hills. These are kind of hacker spaces that are in like the LA, Orange County area. So there's Mag Labs. They're very, I want to say they're mechanical engineering and structural based, but they do have a lot of the tools that I stated in these slides. There's 23B down in Fullerton. Really nice guys. And Null Space Labs, they're up in Burbank. They have a whole bunch of things for all of your electronic desires. They have 3D printers, and I'm involved with this hackerspace, and those are really cool people there. For getting equipment, you can always go to eBay, or there's also liquidation shops. So if there was a lab or an office nearby and they're closing down, they usually just give all their stuff to a liquidation shop, and so you can get those at a good price. Things to keep in mind is a lot of times when you're getting used equipment, it's not going to be calibrated. I don't care too much about this. If you're working in a professional sense, if you're working with very, I guess, high speed or very intricate devices, you might need something that's accurate and calibrated. But we're hacking around, so we don't need to care about that stuff. So resources, Art of Electronics, I highly recommend as a book. They also have a lab book that has much easier language and also pictures, and goes into how different components work in a very easily to consume, very hands-on way. Also, Hacking the Xbox is a very good book, and it's free. So if you go to the publisher's site, No Starch Press, you can go and download it from there. And so he goes into how his process of getting into the Xbox, reverse engineering it, also decrypting the binary, because so not all the time can you just hook things together and pull it off and be home free. A lot of times those are encrypted, and so he goes into detail on that and going through the methods that he uses. Not all of those methods are something that we like someone who's starting out can use, but it's good to explore what someone's doing. Websites, analog.com, Analog Devices has some good guides about things. All About Circuits, that's a new website, and usually if you're looking like, what is I2C and how does it work? If you want more details, they'll probably have it on their website. EEVlog is a really old, it's kind of an old website, but they always have interesting stuff going on, and um, really smart people are always writing some articles on that. So I'd recommend those. For learning components, I haven't really been able to find a good resource for that. You can always, like, as you're looking through stuff, it's what you call a BOM. So it's a build of materials. So you can go through that. You can kind of look on m0zy.com or DigiKey, look up the device and kind of see how it looks like. I think Make has a book of different components electron components that you would usually see. But as far as like a dictionary where you can just kind of look it up by picture, I haven't been able to find a good source. Yeah, so if you guys have any questions, feel free to ask. You can hit me up on my email or at Twitter, or check out my website. I think it's down right now, but yeah, I have some articles on there that you guys can look at. And if, there's other talks that are on TaroHack. So, if you're curious about how would I go about reverse engineering the binary once I have it pulled off of the hardware, I would recommend going to the binary exploitation workshop. It's done by my friend Datagram. He's a really smart guy, really knowledgeable, and I think it's a worthwhile talk for you to attend. Thank you. If you have any questions.
So, yeah, there's one question I wanted to ask you, but it seems like you already answered it about the books or resources. What do you recommend? Okay. That was answered already. So going down the list of the other questions people asked was, someone asked, would it be advantageous to post videos of our own reverse engineering?
I think so. Like I said before, be careful. For the TP link, I don't think I'm going to be having any trouble with that. But if you're reverse engineering like something like Microsoft or Apple, you might get a slap on the hand. Just be careful, be wary what you're doing.
Okay, next question is, how often should we dust our electronics? Is dust something that could damage our hardware if we never clean them?
So yes, and it's not because dust is dangerous. It's mostly because dust can kind of keep your hardware from cooling down appropriately. And when hardware is heated up, it can damage a lot of the materials and traces of the hardware. So I would dust. It depends. Like if you have your desktop on the floor, you'd probably want to dust more often than if it was upraised on a desk. But if you start seeing like a good visible layer, I would try and dust as often as that occurs.
Next question is, this is a personal one. One of my speakers on my Sony Tritron went out and the bottom right side of the screen is discolored. If I wanted to try to open the device to check for damages, what type of precautions should I take for that?
So speakers, they can't, I'm not sure if it's like those big speakers that you usually plug directly into the wall, or if it's like a PC computer. So you'd want to be careful with voltages. You'd want to.
So I think the question was for a CRT TV.
Oh, CRT TV.
Oh yeah,
I'd be careful with that. Like those can be very high powered and have large capacitors. So unplug your TV, kind of leave it there for some time. Like I said before, work out with it with one hand. Some different like multimeters are rated for different voltage levels, so be aware of that as well. Yeah, man, be careful when it comes to high voltage things. I'm too chicken for it, but I'm a chicken, so.
Okay, I think this one should be the last question. How important is static discharge? I've gone into my computer while standing on carpet and swapped out my hard drive, but heard this can be bad, although I never had any issue. How dangerous is this to my hardware?
it's kind of and things happen when they happen. I was working on building up a 3D printer here with carpet, and definitely damaged some parts building that on carpet. It happens when it happens. I would be wary of it. But if you're discharging yourself before you're working on hardware by touching something metal, you should be fine. But if you're wiggling around, like if you're sitting on the couch or wiggling around and working on hardware, you're probably going to be increasing your chances throughout the time that you're working on it. So it really depends. It's like driving down the street. If you drive, you know, if you drive without your glasses, you might be fine. Nothing's going to happen. But there's always that one time where, you can't see.
And that is all the time we have for questions, but it is still possible to ask questions, and m0zy, if she gets a chance, can answer them on the Whova site. If you need help with that, m0zy, just send me an email and help you with how to answer
Okay.
questions on there. And that,
I don't think I'm have an account for Whova, but you guys can always email me too.
or email her at that email.
Or even Discord. I think my handle is the same on Discord.
Mhm. So if you have questions for her, you can, as she said, email her or Discord as well. Other than that, thank you guys for joining this talk.
Yeah, thanks for joining, guys. Have a good one.